Welcome to Beyond the Radio Dial, a wireless innovation forum podcast about the importance of radio spectrum for everyday life. I'm Stephanie Hamill, Marketing Director for the forum. Beyond the Radio Dial is hosted by Andy Clegg, Wind Forum's Chief Technology Officer and self-described spectrum nerd. Now, here's Andy.
Thanks, Stephanie. Hi, all. Welcome to this very first episode of Beyond the Radio Dial. Today, we're focusing on a very important area of definite everyday interest and growing global importance, that is weather and climate. Radio and wireless technologies are used in many ways in those topic areas. So to take a closer look, today we're tuning into Professor Al Gasiewski from the University of Colorado, Boulder. Al is an expert in remote sensing of the Earth's atmosphere and oceans using radio.
He also uses radio spectrum for radar systems that image soil moisture, environmental sensors for renewable energy development, and systems for detecting electrical phenomena in the atmosphere.
Thanks very much for joining us today on Beyond the Radio Dial.
You're welcome, Andy. Great to be here.
Cool. So let's get straight to the questions. And of course, the question of the day is, how is the radio spectrum used in weather and weather forecasting?
In a lot of ways, and they're the sort of obvious ways that have to do with just communication of information. Taking satellite data and downlinking it to our terrestrial environment where we can process it and use it. Taking that data and then distributing it through weather forecasts to your apps on your phones, for instance, as well as all over to aircraft flying, for instance. Taking the data from, for example, weather balloons that we still launch around the planet, and many of them in this country every day, and getting that data down to the ground.
That's actually an interesting fact, Al. And I don't think a lot of people know about this, because there are all these stories about shooting down Chinese balloons over the United States and stuff. But the fact is, every day in the United States, tons of balloons are launched for weather.
That's correct. Yeah. Typically, I don't know exactly the number, but I believe it is something like 80 launches over CONUS per day at 12-hour intervals. And these are measuring temperature, humidity, winds, and sometimes special launches for other parameters as well. And so that all requires communication bandwidth. And then there are a couple of other areas as well. We use the spectrum for radar, and we have a number of sites around the country that are constantly scanning the skies for rain cells, for rain events. Some of these events are severe, some of these are producing tornadoes. And so those spectral bands need to be used for that application as well, for radar. And then finally, there is another area, which happens to be the field that I've been studying for several decades now, which is satellite radiometry. It's literally looking at the Earth at wavelengths that are correct, that are proper for weather forecasting. It's kind of like microwave eyes. If you could see the planet not with red, green, and blue as what we do with our own eyes, but rather with microwave frequencies, you'd see all of the interesting information you need to be able to forecast the atmosphere, the temperature fields, the humidity fields, the rain and the clouds, and then other related parameters as well. So I look at this as seeing the world through microwave eyes.
So you're saying that radio isn't just, the man-made generation of signals, but that the Earth itself generates radio signals naturally, and that's what you're looking at?
Absolutely. Yeah, we call this thermal radiation, and the Earth produces it to various different degrees at various different microwave frequencies. But measuring that naturally emitted thermal radiation, which requires no transmissions on our part, that turns out to be the most critical source of information into numerical weather forecast models today. And if we didn't have that, we'd be set back 20 to 30 years in weather forecasting.
So, you talk about thermal radiation. So the Earth is emitting heat waves and things that we can detect with radio sensors. Well, I have temperature, you have temperature, we all have temperature. Does that mean all of us are also emitting our own radio waves?
Absolutely. Any piece of material, any body at some temperature is emitting not only in the infrared portion of the spectrum, and of course we can see that if we use our little infrared cameras and take pictures of people, they look bright, but they're also emitting in the microwave portion of the spectrum. And so if we use the proper microwave equipment, you could think of it as microwave cameras, then we can detect that radiation. For example, I've got here a piece of hardware that we use in this field of radiometry. It's a very high efficiency narrow beam antenna of the type that we build these microwave cameras out of. And if I scan this across the screen past you, the radiometer that's connected to would register an increase in temperature. And that increase in temperature we see when we have our satellite systems scanning the Earth as well. That produces very useful, very noticeable changes in the microwave emission temperature. And we utilize those in our numerical weather forecast algorithms to predict what the state of the atmosphere is going to be 7 and even 10 days ahead of time.
Interesting. That looked a little bit like Hal's eyeball from 2001 Space Odyssey. Okay, just so anyway, okay. So moving on, so you also do research in understanding the ocean and ocean processes and stuff. Can you talk a little bit about how you use radio to study the ocean?
Oh, yeah. So it's interesting because the ocean is a tremendous source of heat. It's of course, in our era of climate change, it's becoming a sink of heat. But from the standpoint of seasonal variations that produce severe weather, it's a source of heat that drives hurricanes, tropical cyclones. And these events draw their heat from the ocean. And so knowing what the temperature of the ocean is within the surface layer is quite important in being able to understand just how much heat there is available to fuel these very destructive engines. And in fact, it's rather interesting. You can look in the satellite microwave data that are used to measure ocean surface temperature, and you can actually see where a hurricane has passed because it actually draws enough heat out of the ocean to cause the ocean to look a little bit cooler behind it.
That's pretty cool, like a fingerprint of the hurricane going through the ocean.
It's a fingerprint. Cool. And there are other ways as well. There is, for example, the thermohaline circulation that occurs on a global scale that transports heat from the tropics poleward. And that thermohaline circulation is driven by salinity differences. Saline water basically is heavier, and as that tropical water that's warm moves northward and begins to evaporate, it becomes a little more saline, it sinks, and that's what drives this tremendous thermohaline circulation system. And if it weren't for that, we wouldn't have as much heat transported from our tropics up into the higher latitudes. Europe, for example, would have a much colder climate than it does today. And so that salinity is another very major important attribute of the ocean. And we sense that with microwave systems.
Right. Perfect. That's what I was about to ask, that radio plays a role in sensing all of that material as well.
Absolutely. It also plays a role in sensing the speed of wind at the ocean surface. Wow. The faster the wind is at the ocean surface, the more waves and foam and large gravity waves are produced. And those waves change the microwave temperature we see when we look at the ocean surface. This wasn't even known about until, roughly the late 1980s as a concept. And now it's something that we have embodied in our operational satellites to measure yet another important environmental variable. In this case, it's going to be ocean wind speed, ocean surface wind speed.
Interesting.
So yet a third way that the ocean plays a significant role in, of course, not only our climate and our weather, but the way we sense it through microwaves.
Interesting. And radio plays so much of a role in this, and probably something that people don't think about. So fascinating. And on that topic, recently companies like Starlink and Kuiper and OneWeb have started launching thousands of internet capable satellites into orbit. And there's been a lot of talk about all the benefits these bring, obviously bringing internet and things to remote areas. But a question for you is, number one, are there opportunities for using these big constellations for improving remote sensing? And on the other side of the coin, do all these constellations generating all of these radio signals in space, can they potentially negatively impact some of the sensing that you need to do?
Yeah, I'll first take the second part of that question, and it's a very serious one because when we observe the thermal emissions from the Earth, these are extremely small signals. Signals that are 10,000, 100,000 times, a million times smaller than the communication signals that are typically used. And as a result, if the use of the spectrum is not very carefully managed, then it's quite possible that these emissions from all of these satellite transmitters that are doing good things, that are providing connectivity around the globe, but it's possible that those emissions can interfere with the microwave measurements we need for weather forecasting. And it's not a lot of energy that's needed to make that interference such that these weather systems just can't function. So that's a very serious reality these days that we're now having to face. It wasn't at all the situation during the dawn of the satellite era and during the dawn of the passive satellite weather sensing era in the, for example, 1980s or maybe even early 90s. But now it's quite a big concern. And so proper management of the spectrum, ensuring that these satellites don't inadvertently transmit in the bands that are critically needed for weather forecasting, is a very important topic if we wish to keep our ability to forecast weather like we have today.
And when you mention passive, just so our viewers understand, passive refers, we were talking earlier about the Earth and us and everything that has a temperature emitting its own radio waves. That's what you call passive. It isn't involving a radar transmission or anything like that. And those signals, even though everything emits it, are ultimately quite weak.
Exactly. The passive sensing technique is really what we're referring to when we think about satellite weather observations. We're just measuring the radiation that's there passively, you might say. We're not actively transmitting any signals and receiving reflections from those signals. So yes, passive technology, even though it doesn't seem like we're using the spectrum, we truly are, because we need that spectrum to be perfectly quiet to measure the thermal noises that are important for weather forecasting.
Got it.
Now you mentioned earlier, though, what can we possibly do with this plethora of new satellites, these constellations? And there's some very important applications that we could be steering ourselves toward in the use of these satellites as well. And it has to do with information down from our satellite sensors to the ground where we can process it. It turns out one of the biggest bottlenecks in the use of our satellite weather data is the time it takes to get that data down to the ground and the bandwidth available to get it down to the ground. And with these satellite constellations, there are some new opportunities that we could be exploring regarding how we can transmit our observed weather data directly to these satellites and use their connectivity and their networks to get that data down to the ground a lot quicker than we've ever been able to. If we could get that data down to the ground within minutes rather than tens of minutes or sometimes an hour, then that makes all the difference in our being able to use that data in weather forecasting. So I think there's some great opportunities ahead as well.
Okay, so Al, you mentioned earlier, some of the challenges, potential threat of this, proliferation of internet satellites in the sky. But are there other, significant threats to the spectrum environment when it comes to weather forecasting, remote sensing, Earth observation?
Yeah, it's not just the satellite constellations, but it's all of the terrestrial services as well that we're developing at higher and higher frequencies. And it's rather interesting because when you go back into the history of radio, all the way back to the early 1900s, when the first radio transmissions were engineered, and you ask yourself, what is the frequency at which those radio activities were performed? What's the, in other words, spectral occupancy in the radio spectrum? And the answer is that for the past 120 years, that spectral occupancy has been doubling about every 6 years. You could think of this as kind of like a Moore's law. Sometimes people call it Gasiewski's law. I'm not sure about that, but it basically is a trend that's happening, whether you think about, for example, the frequencies at which we're able to transmit, the cost of electronic hardware in constant circa 2024 dollars for transmitting at a certain frequency, transmitting at a certain frequency, or receiving at a certain frequency. Or you could think of it as the frequency at which our national and international agencies are managing contention for the radio spectrum. All of those are such that that frequency is doubling about every 6 years. And so, from the standpoint of the use of radio frequencies for terrestrial purposes, communications, whether it be 5G or future 6G systems, there is a risk that the emissions from those systems are going to be spilling over into the weather satellite sensing bands as well. And when that happens, again, it's a very small amount of spillover. These so-called out-of-band RFI emissions, they can compromise our ability to forecast weather.
Okay. All right, good to know. And then, one final question, not related to, the spectrum challenges, but are there other technical challenges that are facing the remote sensing community when it comes to weather and climate observations?
Well, certainly we are limited by fundamental physical laws regarding just how much time it takes to make a meaningful satellite observation. Those satellite observations, they have to be made at what we call a temperature resolution that's kind of small compared to the average daily temperature fluctuation in the atmosphere. Call it about 1/10 of a degree. If you can't make one of these measurements to within roughly 1/10 of a degree of precision, then that measurement becomes less and less useful. Now, it turns out that this fundamental physical law not only requires a certain amount of what we call integration time, or time to stare at the atmosphere, but it also requires a certain amount of bandwidth. And the greater the integration time, the greater the bandwidth, the more precise that measurement can be made, and bringing it down to that 1/10 of a degree or better level is critical for satellite weather forecasting. And so bandwidth does play a role. We can't just use infinitesimally narrow bands. Those bands have to be wide enough to permit the use of these satellite sensors. And so there's a fundamental technical challenge in being able always to meet that particular fundamental physical sensitivity limit. We know how to do that as good engineers, and of course, we're always building our systems to do that. But there's another area of technology growth that can help us here. Rather than having just a single sensor, or maybe 2 or 3 such sensors for different times of the day in orbit, you can imagine what would happen now if we had 50 or 60 or 100 such sensors. Then all of a sudden that time, that integration time, can be increased by that factor of 50 or 60 or 100. And when that happens, then we have the ability of more precisely seeing the planet's emission temperatures, and therefore more precisely forecasting. And this is a future possibility that we're now exploring. I'm working on this, for example, through a company, Orbital Microsystems, that's developing this constellation of satellites. And we hope to see this constellation actually improving our weather forecasts as we go ahead into the future. But it all hinges on the availability of quiet spectrum to use of these bandwidths that are relevant for weather forecasting.
So you're trying to develop your own swarm, massive constellation, but you're trying to do it not to emit radio signals, but just to listen to the very faint ones that are there. Interesting.
Absolutely. It's a small constellation, comparatively speaking, and it doesn't emit at all. But it could very well benefit from the use of the other communication system constellations in getting its data down quickly.
Interesting. All right. Well, I think that's about all the time we have for this episode, Al. We thank you very much for joining us. I hope the forecast for your work continues to be bright and sunny. Thanks also to our viewers. Please stay tuned for future episodes of Beyond the Radio Dial. We have several in the works right now, and we'll post those as they become available. So thanks again, Al, and Appreciate you coming by.
My pleasure, Andy. Thanks a lot.